Rocket Lab just broke ground on Launch Complex 3 at Wallops Island, while their Neutron rocket nears debut, completing in 4 to 5 years what Blue Origin couldn't finish in over a decade. New Glenn faces another avionics failure as Rocket Lab secures military contracts previously reserved for industry giants. The numbers don't lie. 60-plus successful Electron missions versus Blue Origin's endless delays. This isn't speculation. It's documented execution versus broken promises. Let's dive right in. Here's what nobody talks about. While Jeff Bezos spent $10 billion building Blue Origin into a 10,000-person workforce, Rocket Lab did something nobody expected. They actually started launching rockets. The timeline tells the brutal truth. Blue Origin, founded in 2000, that's 25 years of development with New Glenn promised for over a decade, still grounded. Meanwhile, Rocket Lab's Electron rocket has completed 60-plus successful missions since 2017. Those aren't just numbers. They represent real payloads delivered for real customers who paid real money. This track record caught the attention of someone who could change everything. Peter Beck, Rocket Lab's CEO, who made a calculated bet that would either elevate his company to SpaceX's level or destroy it completely. While Blue Origin burned through billions on New Glenn's endless redesigns, Beck did something audacious. He authorized construction of Launch Complex 3 at Wallops Island for just $50 million. To put that in perspective, Blue Origin has spent an estimated $3 billion on New Glenn development with 0 orbital flights to show for it. But Complex 3 isn't just another launch pad, it's a strategic weapon. This facility can handle Neutron's 13,000-kilogram payload capacity with automated systems designed for rapid turnaround. While SpaceX revolutionized reusability, they're still constrained by shared facilities and complex scheduling. Rocket Lab built their own dedicated playground where they control every variable. The engineering specifications reveal the deeper strategy. Complex 3 features automated first-stage recovery systems that can process return boosters faster than current industry standards. This infrastructure advantage led to an even bigger victory that blindsided the entire space community. December 2024 delivered a bombshell. U.S. Space Force announced Rocket Lab as an approved national security space launch provider. These are the same prestigious contracts that took SpaceX years to secure, and the same program Blue Origin has been pursuing since 2019 without success. How did a company with a fraction of Blue Origin's resources leapfrog a $15 billion giant? The answer comes down to one critical factor: demonstrated reliability. Military contracts require proven performance, not promises. SpaceX earned their certification through 200-plus consecutive successful launches. Rocket Lab earned theirs through 60-plus missions, with 0 total mission failures since 2018. Blue Origin? They're still explaining why New Glenn can't maintain a launch schedule. The financial implications are massive. National security launch contracts average $150 to $400 million per mission. Rocket Lab just secured access to a revenue stream that could fund their entire operation for the next decade. More importantly, this government backing validates their technology in ways that marketing campaigns never could. This military endorsement set the stage for Rocket Lab's next masterstroke, a technical achievement that exposed Blue Origin's fundamental approach problems. Here's where Rocket Lab delivered a masterclass in smart engineering. While Blue Origin's New Glenn relies on traditional aluminum construction with separate fairings that fall into the ocean, Neutron pioneered an integrated carbon fiber design that recovers everything. The hungry Hippo fairing system represents pure engineering elegance. Instead of jettisoning expensive fairings worth $5 to $10 million each, Neutron's fairing splits open like a clamshell, releases the payload, then closes for recovery with the first stage. No fairing recovery ships, no complex ocean operations, no lost hardware. Traditional rocket companies treat fairings as expendable because recovery is so difficult. SpaceX catches some fairings with specialized ships and nets, an impressive but complex operation. Rocket Lab eliminated the entire problem through integrated design. When your fairing is permanently attached to your reusable first stage, recovery becomes automatic. But this surface-level innovation masked a deeper technical revolution that even industry experts initially missed. Neutron's Archimedes engines began as simple gas generator designs, reliable, cost-effective, and proven. Then Beck made a decision that shocked aerospace veterans: pivot to full-flow stage combustion, the most complex engine cycle in rocketry. This is the same technology SpaceX uses in their Raptor engines and the same approach Blue Origin planned for New Glen's BE-4 engines. The difference? Rocket Lab developed their version in just 18 months, while Blue Origin spent 8 years on BE-4 development and still faces reliability issues. Full-flow staged combustion delivers 15 to 20% better efficiency than gas generator cycles. For Neutron, that translates to 2 to 3 additional tons of payload capacity. In launch economics, those extra tons represent millions in additional revenue per mission. Early test results validate Beck's bold decision. Archimedes engines completed full-duration burns at 100% thrust with 0 anomalies. Compare that to New Glen's recent launch scrub, caused by booster avionics failures, the kind of basic systems integration problems that should be solved after a decade of development. This technical success highlighted the most damaging contrast between the two companies: their completely different approaches to development speed. From Neutron concept to launch complex construction, 4 years. From New Glenn concept to first launch attempt, 12 plus years and counting. This isn't about rushing to market, it's about methodical execution versus endless perfectionism. Rocket Lab proved their development philosophy with Electron: design, test, iterate, scale systematically. They're applying the same proven methodology to Neutron with predictable results. The development timeline reveals fundamental cultural differences. Blue Origin announced New Glenn in 2016 with a 2020 launch target. 7 delays later, they're still troubleshooting basic systems that competitors solved years ago. Rocket Lab announced Neutron in 2021 with a 2024 launch target, and they're actually ahead of schedule. Beck's team employs incremental development with continuous validation. Every Neutron component undergoes extensive ground testing before integration. Every system proves itself independently before final assembly. When problems arise, they're identified and solved quickly rather than triggering months of analysis paralysis. The result? When Neutron finally launches, it won't be an experimental prototype crossing fingers for success. It will be a thoroughly validated system ready for immediate commercial operations. This execution advantage becomes even more powerful when you examine what customers actually want in today's market. Commercial launch demand exceeded supply by 40% in 2024, with customers paying premium prices for reliable access to space. SpaceX captures most of this demand because they deliver consistent performance month after month. Blue Origin positioned New Glenn to compete directly with Falcon 9's 22-ton payload capacity. A logical strategy except for one fatal flaw: they never reached orbit to prove their capability. Meanwhile, Rocket Lab identified and targeted the underserved medium lift market with Neutron's 13-ton capacity. The addressable market for medium lift missions exceeds $4 billion annually. Constellation deployment, military missions, commercial satellites, all require the reliability that only comes from proven flight heritage. Neutron will provide exactly that capability from day one, built on Electron's demonstrated track record. Customer feedback validates this approach. Multiple commercial clients have already signed Neutron launch contracts based purely on Rocket Lab's Electron performance. They're buying trust earned through consistent execution, not marketing promises about future capabilities. This market insight reveals a deeper truth about Jeff Bezos' fundamental miscalculation in the space business. Jeff Bezos built Blue Origin on a premise that works in many industries. Unlimited resources plus brilliant engineering equals market dominance. The formula succeeded with Amazon's retail empire and AWS cloud services. Rocket launches operate by different rules. Space missions require something money can't buy: operational experience. Every launch teaches irreplaceable lessons about systems integration, weather constraints, payload interfaces, and recovery operations. SpaceX learned through 200-plus missions. Rocket Lab absorbed these lessons through 60-plus flights. Blue Origin remains stuck learning through simulations and ground tests. The cultural difference shows in public statements. Bezos talks about lunar colonies and space manufacturing, visionary concepts decades away from reality. Beck talks about reducing launch costs and improving reliability for today's customers. One sounds inspirational, the other sounds like someone who understands the actual business. Beck's philosophy reflects hard-earned wisdom. Master your current market before conquering new frontiers. Prove reliability at achievable scale, then expand systematically. Build customer trust through performance, not presentations. The financial results speak volumes. Rocket Lab trades at realistic valuations based on demonstrated revenue from actual launches. Blue Origin remains a private company burning Bezos's personal fortune with no clear path to profitability or even orbital capability. Three powerful forces are converging to accelerate Rocket Lab's advantage. First, Neutron's 2025 debut will double their addressable market overnight, moving from small satellites to major commercial missions. Second, Launch Complex 3 enables launch cadence previously impossible for medium-lift rockets. Third, military contracts provide revenue stability that purely commercial companies can't match. Blue Origin faces the opposite trajectory. New Glenn delays push first commercial missions into 2026 at the earliest, assuming no additional technical problems. Customer confidence erodes with each postponed launch window, making recovery exponentially harder as competitors establish market dominance. The space industry rewards consistency above all else. Customers pay premium prices for reliable partners because launch failures destroy billion-dollar payloads. Rocket Lab built that reputation systematically through 60-plus successful missions. Blue Origin is still trying to establish basic credibility after 25 years of development. Beck recently stated that Neutron could achieve monthly launch cadence by 2027. Based on Electron's demonstrated performance and Rocket Lab's track record of meeting targets, that's not marketing hype. It's operational planning backed by proven systems and dedicated infrastructure. The question facing the industry isn't whether Rocket Lab will succeed in challenging SpaceX's dominance. The question is whether Blue Origin can recover from falling this catastrophically behind a competitor they probably never saw coming. This is exactly why execution beats billions in funding. Rocket Lab proved that smart engineering and consistent delivery outperform celebrity backing and unlimited budgets. They've made space access a reliable business, not a billionaire's experiment. The real impact? Space exploration just became more competitive and affordable. When smaller companies can challenge giants through merit alone, everyone benefits from faster innovation and lower costs. Neutron's 2025 launch will trigger the next wave of competition. Blue Origin faces a critical decision: adapt Rocket Lab's execution-focused approach or fall further behind. Can Blue Origin recover from this setback? Drop your prediction in the comments below. I read every single one. This is Space Hub. Hit that like button if this analysis helped you understand what's really happening in space. Subscribe and ring the notification bell so you never miss our deep dive breakdowns of the biggest space developments. The space race is accelerating, and the companies that execute fastest will define humanity's future among the stars. SpaceX just revealed upgraded Raptor 3 engines at Star Factory, and the performance gap with China's Copycat attempts is staggering. Chinese company Arctic's Mammoth 1 engine produces only 163 tons of thrust, while SpaceX's Raptor 3 delivers 280 tons using advanced welded joints. That's barely matching SpaceX's original Raptor 1 from years ago. Recent upgrades after SpaceX's May testing incident show sophisticated solutions Chinese manufacturers can't replicate. Let's dive right in. To understand why Chinese copycats are falling so far behind, we need to examine what happened at SpaceX's McGregor facility in May. That testing incident wasn't an accident. It was a deliberate stress test that revealed exactly what SpaceX needed to fix. During this test, engineers pushed Raptor 3 toward 300 tons of thrust, far beyond normal operating parameters. The engine exploded, but this failure provided crucial data about structural limits in combustion dynamics. SpaceX was specifically testing the methane to oxygen mixture ratio, a process requiring millisecond precision where even tiny errors trigger what Elon Musk calls a hard start. What separates SpaceX from copycat manufacturers is their response to failure. Instead of viewing the explosion as a setback, they analyzed the failure data and implemented 3 critical upgrades. These improvements reveal sophisticated engineering solutions that Chinese manufacturers cannot replicate simply by copying external appearances. The upgrades visible on Raptor 3S and 20 demonstrate why surface-level copying fails to achieve real performance gains. The gray collar innovation. The most noticeable addition is a gray protective collar around the Methalox feed line joint. This component serves as a vibration dampening system designed to withstand forces from 280 tons of thrust. The full-flow stage combustion cycle generates intense vibrations that can damage joints over multiple firing cycles. Chinese engineers photographing earlier Raptor versions would see this collar but lack the engineering data needed to understand its specifications. They're copying visual elements without comprehending the underlying physics that determines collar thickness, material properties, and mounting configurations. Advanced turbopump protection. SpaceX also added a metal casing around the methane turbopump assembly. This housing provides multiple functions: debris protection, thermal management, and electromagnetic interference shielding. The casing design requires detailed understanding of heat transfer coefficients, vibration frequency analysis, and electromagnetic field interactions. When you examine ArcT's Mammoth 1 engine, you'll notice the absence of such sophisticated protective systems. They've replicated the basic turbopump layout, but missed the critical protection mechanisms that ensure operational reliability. The welded joint breakthrough. The most significant upgrade involves replacing bolted flange connections with precision welded joints between the thrust chamber and hot gas manifold. This engineering change delivers multiple performance improvements: weight reduction of 75 kilograms per engine, elimination of potential leak paths, enhanced gas flow characteristics, superior structural integrity under extreme pressure. This welding process requires joining different metal alloys, copper for the combustion chamber, and Inconel for the manifold. The metallurgical expertise needed for this transition explains why Chinese manufacturers continue using heavier, less reliable bolted connections. Based